EEE 145, Chapter 5, Relay Input Sources. Okay, so now we're going to go ahead and talk about how do the relays itself get the voltage and current measurements from the system, right? We talked earlier that we have some type of instrumentation transformer that will help us do that. So let's first go ahead and start talking about how to transform the current. So in the power systems, we need ears and eyes to understand what's going on. And one of the important quantities we need to understand a power system is, let's do that, current. Okay. Current is very vital to know the loading factor of the system and for fault detections as well. Okay. Now, in a nominal system, what type of current levels will we see? So what in the ideal world? On the transmission side, just to give you some ballpark ranges, you could expect somewhere around 100 amps to 300 amps, right? It's not going to be that big because the voltage is very high. So you need lower amount of current to send power across long distances. And that's by design, because the lower the current, the lower the losses on the power line. Next, we have distribution. Okay, so distribution is more of the residential area. Those feeders can range as small as about 200 amps to more than 1,000 if you have a pretty big feeder, right? It all depends on how many houses and how many loads you have on that particular feeder. And then kind of a special case outside utility is industrial settings, because some of you guys will end up working for plants. Industrial centers are like distribution, but much more dense, much bigger loads like giant motors. So again, that could be as small as 200 amps, which is a few motors, some heaters and lights, all the way to like 4,000 amps or more because you're running a bunch of big motors nearby. Okay, so those are the three current levels we're going to see. So we need to make sure that we have devices that can fit these type of currents. Now, the big problem with these currents is they're very big, very dangerous. So the next question is, what are safe metering levels that humans can interact with? And even if we get shocked, we're not going to kill ourselves. Well, we kind of made a standard about 5 amps at 120 volts is about the standard. Okay. Right. Just to give you an idea, your household socket has 120 volts. And the load for your room, that socket is most likely 15 amps. So it's about the same level as your lamp and your microwave and your basic household appliances. Okay. Now, 1,000 amps and 5 amps are very big difference. So we need some type of intermediate device to change 1,000 amps down to 5 amps. Right. And what would that be called? That's an instrumentation transformer. Instrumentation transformers. As you remember, a transformer can lower or increase the current or voltage levels, and we want to lower it to a safe human levels for metering and for us to interact with, and that's called instrumentation levels. So that's why we're all called instrumentation transformers. And specifically for current, we use a current transformer. Or a CT for short. Okay, so this is what we're going to be talking about today, current transformer. Okay, so let's put some stars. This is an important thing. Okay, so now let's keep on going. Well, what does a current transformer look like, right? So there's several types of current transformers you'll see. The top one here, these are called donut type transformers. And just, looking at it, it's originally the ones were round and you put a cable through it. So it kind of looks like a donut CT, right? So you can see right here on the left-hand side, you can see the major cable going through the cylindrical CT, hence the hole in the donut. Next, we're going to have current transformers on breakers. So this right here, let me draw it accurately. This thing right here, That is a breaker. Okay, we saw a few pictures before. Just remind yourself, this is the breaker itself. That's the control panel for the breaker. And on top of it are the CTs, these round cylindrical devices. Let me get a highlight for you. Okay, this thing right here. These are the CTs. Again, you can kind of see they're round, kind of like a donut, but we slip them on the bushings of the breaker. So these are called slip-on CTs, right? Because they slip on the bushing of a circuit breaker. So typically any big circuit breaker or transformers, we're going to put some CTs on the bushings. It's just a nice convenient place to put it. Now, if we don't have the luxury of the cable being accessible to put the donut on through, or a breaker or a transformer to put slip-on CTs, we're going to need something called a standalone CT. Right? So this one right here, this device is literally just put in the yard because there's no other structures for us to put our CTs on, and it's a self-sufficient one. Right? Obviously, the standalone CT is going to be a little more expensive because you got the insulators and frame and a lot more extra things you have to add versus just literally a slip-on CT where, you know, it's just less material. Okay, so those are the three major type of CTs you're going to see in the distribution side, or the utility side rather, right? So next, let's go and talk about how do they operate? What's the principles that they run off of? So number one, how is the magnetic field generated in CT? Because remember, the transformer part should automatically tell you that there's some level of magnetic field flowing through it, okay? So you have the primary line, which is a big bar going through the donut. So primary line current flows, and use the right-hand rule, you can create, it causes a magnetic field. Field to flow in this iron CT core, all right? Now, as current flows through, we're going to induce a magnetic field flowing inside the metal core in a circular direction. And then the next question is what causes current to flow through the secondary winding to the relay? Okay, so this is what we mean by secondary winding right here. Okay. Well, remember, we have a magnetic field flowing through the CT core. So the same magnetic field will induce current in the secondary windings, right? Remember, if you can see right here, notice that there's a bunch of coils right here, okay? These coils is what the magnetic field will flow through and produce a certain amount of current. And you can look at your turns ratio where the primary current has a turn of 1 and the secondary side has many turns like 20, 30, 50. And then you could see a relationship between the current. Okay. So kind of going with that, let's talk about that ratio. Now, just a reminder, the typical primary line current can range from low current. So low current, which can be as small as 50 amps, to, so it could be back and forth, fault current, as large as 60,000 amps, so 60 kiloamps. Okay, so there's a very wide range we have to kind of be acceptable to, right? Now in the secondary circuit, what's the range of values you can expect? Or the minimum level a relay can realistically pick up is 0.1 amps. Anything below 0.1 amps, the relay it's not sensitive enough to pick this up. Okay. A protective relay, I would say. A metering relay for money will probably be able to pick that up because they're very, very accurate. And money matters a lot. Okay. Nominal, so kind of everyday normal expectations is we expect about 5 amps flowing through the secondary. Okay. And of course, the maximum we could realistically take during fault levels is 100 amps. So these are the kind of ranges where 5 amps is expected, and we designed for that. And 100, anything above 100 amps is unacceptable in the fault. So we need to redesign it or change the CT or something. Okay. So the question is how do we relate these two? Well, we have something called a current transformer ratio, or CTR. This is basically the turns ratio of the transformer. Now we're going to simplify it. We don't have to go to N1 and N2s. We just literally call it a CT ratio. And we say that the CT ratio is the primary current, I primary, divided by I secondary. Very simple. Okay. And I would say this one, the primary current varies by design. Right, so it's whatever a power system was designed for. It could be 50 amps, 100 amps, 2000 amps. That primary current is based on the circuit itself, but the secondary current is typically standardized to 5 amps. Okay, so when we do our calculations, we could think, well, if I want a CTR, I know my I secondary should be 5 amps. Let me calculate what my primary current is going to be, and that's my CT ratio. Okay. So the big thing here is look at your mins, look at your maxes, figure out the CT ratios. That's the gist of designing a CT. All right, just a little image down here. You can see, let's color code this. This is your primary side. And then down here is your secondary side right here. All right, so you can see your primary circuit and your secondary circuit, and you have 2 currents flowing through each of them. Okay. So let's go through a quick example that I'll do just to show you, how do we crunch numbers, right? So if you look at this diagram, this thing right here, this is your CT. This is your CT ratio. Okay, so this is a CT in questions. The circle with the R, that's a relay. So this is a relay. And this one down here is a circuit breaker. Okay, but for our sakes right here, this is a CT right here. Okay, you get your primary current going through. I should probably say also, if you're not familiar with the little symbols, this little arrow at the bottom just means load / houses. Okay, so just you have a line going down, this is your load, and then current just flows towards the load. Up here, this is your bus. So this is your source bus. So some level above here is the transformer sending energy through. We're a feeder going through where we have a circuit breaker, and the circuit breaker can be controlled by the relay, and the relay is getting its input from the CT, which is what we're looking at. So look right here, 600 to 5. I know this is my CT ratio, so I can really write here CTR is equal to 600 to 5. Okay, remember how we talked about 5 amps is standardized? So you have 5 amps over here. So if we have 5 amps flowing through the relay, we must have 600 amps flowing through the primary to make the current transformer equal, right? Now, there's a standard that you just keep the 5 on the bottom because it's easier to read. So I see 600 to 5. I know my primary current should be about 600 amps. Okay. You can technically go and just do the math and just call this 120, right? But you kind of lose some information. Most people in the world like to keep it 600 to 5 because it's easy to look at 600 and say, oh, well, that should be the current flowing through. Okay. Now remember, we said that 5 amps is standard, so we shouldn't really have more than 600 amps flowing through it. If you have more than 600 amps, you should probably downsize it. That's for more complicated things to talk about. So here we got a CTR of 120. I want to find my secondary current. Well, remember, CTR is always my I primary over my I secondary. Okay. Now we could rearrange this where I have an I secondary is equal to I primary divided by CTR. So we go ahead and do our math. Our primary is 600. Our CTR is 120. So our secondary, we should do the math, is 5 amps. Okay. So if I have 600 amps flowing through the circuit, I expect 5 amps flowing through the relay, which is by design. Remember, this is our standard. We always want to make sure we have 5 amps. As we want to get as close as possible to 5 amps flowing through the relay. Okay. Now, what if our primary current is 2400 amps now? So it kind of changed a little bit. Right. So maybe we add in more loading. So we need to figure out what our secondary current is at this rate. So I have my CTR. This is 600 to 5 or 120. Okay, remember, this is by design. We can't change this easily. Okay. Now, let's go ahead and look at our secondary current, I secondary. This is I primary divided by CTR. In our case, it's 2400 amps divided by 120, which is 20 amps. Okay. So this is kind of too high. So this kind of has it rings some alarm bells for me. So either we have a fault going on or we incorrectly size the CT, right? So out of all this, there's 2 combinations. Either one, there's a fault on the system causing too much current, or 2, our CT ratio is too small. Now, what's the solution? If we have a fault on the system, the solution for that is to open the circuit breaker, open the CB to extinguish a fault. If my CTR is too small, we'll I have to purchase a bigger CT. So we need a bigger CT. Okay. Now, looking at this, if I have 2400 amps, what will be my bigger CT? Well, the easiest one is just to get 2400 to 5 CT, but those might not exist. So we might have to talk to manufacturer. They'll probably point us to a 2500 to 5 CT, right? So unfortunately, won't be able to get when you do this calculation, you won't ever be able to get exact, 2400 over 5. You might just have to step it up a little bit to 2500 over 5. It really could. Manufacturers typically give you these in like set ranges: 2000, 2500, 3000, 3500, 4000, and so on, right? You can't dial into 200 3826, right? And this is fine, right? You're only 100 amps off. It'll be a little bit lower. We're okay with that. So those are your 2 solutions in case you have too much current. Okay, so now let's talk about within the CT when you're installing them for ease of use. They have taps on them to change the CT ratio in the field. So if you notice, our nominal ratio is 2005. So this is a 2005 CT ratio if we're using full windings. So if using all the windings. Okay. Now, what do I mean by using all the windings? Let's find out. What terminals should I connect the secondary side to form, what terminal should I connect the secondary side to form a CT with a 2005 ratio? Right, so here, well, I want 2005. Now, if I number crunch this is 400 turns. So I got to look at this, and between X1 and X2, there's 80 turns. X2, X3, there's 160 turns. So how many of these turns do I need to eventually make 400? Well, I have 80 turns. That's not enough. So let's look at 160. Okay, that's still not enough. So that's what, 240? I could add another 60. That's 200. So 240 plus a 60 is 300. That's still not enough. I could put another 100 turns. I can add them all together, and that's going to be 400. Okay, so in this particular case, I need to use X1 all the way to X5. So we use these connections. Because now we're going to use the full winding. So what does that mean here? Well, if I would literally go out on this into the field, hard connect the wire to the X1 terminal, and then bring that out to the relay. And then out from the relay back to the CT, I will connect it to X5 right here. So you can see how we're going to use all the turns because the current is going to flow here, and it's going to use all the turns like this. And then you can just add up turns. You have a 2005 CT. Now, what would happen if I wanted 805 CT? Right? For sure, I'm not going to use X1 to X5 because that's 2005. That's vastly incorrect. Well, let's do the same thing again. I'll have an 800 to 5. All right, let's go ahead and see what's the actual ratio, the turns ratio of that. So that's going to be 160. Okay. Now, if you look over here, conveniently, where they have that, that's just between X2 and X3 is 160 turns itself. So let's go ahead and use this. Let me redraw this a little bit. So let's say we'll use connections X2 and X3. Okay. So again, if we're going to hook up a relay, let's just hook up the relay wires to X2 and X3, and we have 160 turns, which is 805. So a lot of CTs nowadays have these multi-tap ratios just for ease of use. That way, when you buy a big CT, you can always tap it down to something more specific for your individual company. Okay. They're pretty popular in today's world, so you should expect to see these pretty often. You might get lucky where one tap does it, or you might have to use a combination of 2 or 3 taps to get the desired CT ratio. But they carefully chose these to give you a wide range of them, right? Typically, when you buy these, there's going to be a little chart, and the chart would tell you, well, X2 to X5 is one ratio, X1 to X4 is another, and it will give you a little table so you know which terminals to connect your relay to. Okay. So let's go ahead and take a 20-minute break for you to work a problem to kind of solidify all this. So it's a 2-part problem. The first part is I'm giving you a circuit. You have a CT ratio. You need to tell me, design that CT ratio to be correct. So remember, we have a 1200 amps flowing through the feeder. You want a specific amount of current going through the relay at all times. You figure out the CT ratio to make that happen. You could look at the slides above for details. Part 2 is, now that you have the CT ratio, which taps would you connect to make sure the relay can see that specific CT ratio? Okay, so why don't you go ahead and do these 2? We're going to come back in 20 minutes and see what you did. So see you guys in a second. Okay, welcome back. So let's go ahead and look at this current transformer design example. So remember the first thing we said, yes, last time there's 1200 amps primary low current flowing through. When you calculate a CTR, ideally, we always want your secondary current to be 5 amps. So if you do your CTR as primary over secondary, you will have a 1200 to 5 CT. Or if you want to put into pure turns ratio, to a 240 to 1. Okay, so the manufacturer asks you, 1200 to 5 is what I need. Okay, so you can see, typically you just look at your low current, just try and match as much as possible to CT ratio for the top number. That's really what you do. Now, we have a 205 CT. Let's go ahead and look at the CT we bought. So let's say our utility we just only buy these CTs. We have like 50 of them. So I need you to make 1200 to 5 ratio out of this 2005 CT. Well, our CT ratio is going to be 240. So we got to ask ourselves, well, what numbers, turns ratios that are side by side will eventually equal 240. Well, we have 80 in the first one and then 160 in the second. So we add both those together, we have 240 to 1 turns ratio, which is equivalent to our 1205. So in this particular case, this relay, we would take X1 and X3. So I would take my relay, here's my relay. I would draw from X1 wire to X3 wire, and this should be my 1200 to 5 CT ratio. So pretty much what we're going to do all the time when we're out on the field and designing it is choose the correct X1 to X5 ratios for your CT ratio. Okay, so let's keep on going about CTs. So the main thing I wanted you to get out of this so far is CTs exist and they're on the system. They need a ratio we need to design a ratio for them called a CT ratio. And then we need to use the taps on the CT to select the correct ratio. The next thing we need to start talking about are two things: the polarity markings and the secondary circuit itself. Okay. Now, one polarity marker has always kind of been a confusion for a lot of people in transformers. In a power system, we don't like confusion, so we try to make this as simple as possible for you. So there's a key rule. So everybody pretty much remember this jingle. Current flowing into the primary dot equals current flowing out of the secondary dot. Okay, so you can see if current flows, she's green. If current is flowing into the dot here, this means current flows out of the dot on the secondary side. Okay, so all CTs are made this way, and then that current will flow in a loop to the relay and back to the CT negative terminal. Okay, so that's just dot convention. Remember, primary current flows into the primary dot, secondary current flows out of the secondary dot. Okay, now once you're inside the secondary circuit, there's two major currents we're going to look at. The first one is your excitation circuit current, IE, right? Excitation current, as it says, excites the transformer, excites the magnetic field to be exact. Field inside the relay, inside the CT, inside the CT core. Now, it's good to note that this current stays in the CT. Okay, notice that we have a separate winding, the XM coil, where the excitation current just flows endlessly inside the CT. Okay, this is just a tax we have to pay for any transformer or anything with magnetic field. A certain amount of leakage current or excitation current is needed just to power the unit itself. What's left flows out of the CT itself and goes to the rest of the circuit. So you can see right here, this dotted line, this is the border of the CT. So anything to the left is internal. This is an internal to the CT. Anything to the right is external circuit, okay? So first one's internal to the CT. So here, the secondary current will flow through the small resistance in the actual terminal itself. So like the CT itself has little screw terminals. There's a little bit of resistance for that we have to account for. And once it comes out, you have the wires and the relay itself, okay? So secondary current, it flows out of the CT windings and through the wires and relays. Okay, now these wires can be pretty long because remember, if you ever go to a substation, the control building could be 200 feet away from the actual breaker itself. So you need to account for 200 feet of wire one way and another 200 feet of wire going back the other way. Okay, so kind of if I want to draw over here, think of your secondary current is going to flow out, hit the top wire, the wire to the relay, RV, this is relay right here. And then it's going to flow back again through the wires to the CT itself. So think about the wires, you have to think about the path going to the relay and back. Okay, so kind of let's show an example of quantifying all this, right? So we're talking about a current, we got some resistors, right? We call this the CT burden. This is a very important part of CTs is how much load can the CTs handle before the CTs burn up, right? Or stop working correctly. Because every resistor, RL, RB, RCT, these are all loads, okay? And each load takes a certain amount of power to operate. So how do we figure out this limit? Well, we have to calculate for it. We have to design this accordingly. So we assume 5 amps standard is flowing through the circuit. And we want to make sure we don't overload it. Do not overload. What I mean by overload is too much power. Okay. So there's only a certain amount of power that the CT can output before it stops working. So we just need to make sure the wire, we don't have too much wire length. We don't have too many relays attached to the circuit that we kind of bog down the CT. What would happen if we exceed the burden of the circuit? Right? So again, burden is how much it can take. If we exceed it, we overload the CT. We overload the CT and go into saturation. So any type of transformer, anything with coils, if you ask too much of it, it's going to saturate the actual transformer, or in this case, saturate the CT. And then this will lead to CT errors, meaning that our CTR will not work, will be inaccurate. Okay. Meaning, so this is bad because the relay won't get the correct information, and it's like you just blinded yourself from the decision-making process. So definitely this is a big issue. Don't let your CTs go into saturation, and we could design for that by making sure the CT is big enough, is beefy enough to take that amount of power. So how can we do this? Well, we need to do some calculations. We need to calculate the CT burden and choose the correct CT class or burden. Okay, so we have a lot of design parameters and specific types of transformers, CT transformers, to make sure that we have that adequate power of what we need. Okay, so let's go ahead and again see an example of how do we calculate it, what does it mean, and how do we find, when we're talking to a manufacturer, what type of information do they need? Well, the first thing we need is we need to know what's the total burden of CTs. Now, there's 2 ways we could do this. We could use it by calculating the ohms or by calculating the power itself. Either one will work. I don't know why that's there. That's fine. So what is the total burden seen in ohms? Well, it's a single loop circuit. So think about the current is just going to come out here through this wire, through the relay, and come back. Okay. So we need to account for the wires, the wire resistance to the relay, wire resistance from the relay, the relay itself, and the internal resistance of the CT itself. Now it's one big loop, so it should be pretty easy. You just add them all together, resistors in series, right? So my R total is going to be RCT, which is 0.5 ohms, plus RL going to the relay, which is another 0.25 ohms. The relay itself has a 1 ohm burden, and the return wire going back is 0.25 again. So my R total is 2 ohms, and this is my burden in ohms. So if you tell a manufacturer, hey, I calculate my burden is 2 ohms, they'll know exactly what to do and they'll point you in the right direction. Another way to do this is you could figure out the power. How much power is drawing from the CT? Well, that's easy. It's in volt ampere. So you know S is volts times amps, or we can use Ohm's law to say it's I squared times R. Okay. And in this case, remember, we typically say we have 5 amps standard. So we make sure our current is 5 amps. We square that. What's the resistance of the circuit? Well, that is 2 ohms. We just figured it out. So we number crunch this. The burden for this circuit is 50 volt amperes. So there's 2 ways to think about this, either in power or ohms. Okay, and when you talk to manufacturer, to them, this is equivalent. If you say 2 ohms, they automatically know 50 volt amperes because they can do a simple calculation in their head. Okay, so how does that play into the accuracy class? Well, here we have charts. So IEEE has pretty much said across the board, these are standard CTs we're going to have. These are the burdens. All manufacturers follow these. So the previous problem, what type of designation do we need? Well, we know we have 50 volt amperes. That's our burden. Well, we could look up here where I have volt amperes on this column. I see 50 right here. So this means this row right here is the type of relay I want. That looks a little messy. Let's kind of see if I can make that a little bit thinner. Okay. So 50 amps right here. This is my B2 burden. So when I talk to manufacturer, I could just straight up say, I want a B2 relay. So B2 designation. So the lingo will be, hey, I'm designing a new power system. I need a 2005 CT multi-ratio, like a previous problem, and I did my burden calcs. I need a B2 designation. And they're gonna be like, oh, okay, I got you, right? Now, sometimes people won't use the B2 burden designation. They'll use something called a CT classification. So then it's just a cross-reference where we say, oh, well, I calculate B2. The standard burden here is equivalent to what we call a C200 relay. So we have a C-class relay, and in our particular case, we get a C200 class CT. And literally, they'll have 200, 400, 800, 100. All CT manufacturers have all these just on the shelves ready to go. Okay, so that's your accuracy class and burden discussion. Okay, so let's keep on going. Here in the for CTs, in the power systems, remember we have 3 phase. 3 phase equals 3 wires. So it's not just one CT for the entire power system. We actually have 3 CTs. Now, anytime we have 3 devices, we always have to ask ourselves, are you going to connect them in delta or Y formation? Okay, in this particular case here, our CTs, we could choose delta to Y connections. This is a Y connection right here because you could tell that the neutral is all wired together. That's a telltale sign. The other side is a delta connection, and you can see that there's no common node for neutrals. It kind of goes around in a triangle. This is just another way to draw the little triangle shape that we know so well for delta. Now, in the power systems, which one do we typically see? 90%, probably even more like 95%, are Y-connected CTs. Okay. It's just Y connections are so much easier than delta connections. We just decide, let's just make our lives easier. Now, if you find an old power system and you see a old mechanical a substation, you might see a delta to Y transformer set up at your distribution substation with old mechanical relays. Mechanical relays. You might see a delta CT connection there. Right? This is something from the 1950s, and it was a trick to correct phase angle of a delta to Y transformer. Remember, a delta to Y transformer has a 30-degree phase shift from one side to the other. We needed a quick and dirty way to correct that phase shift, and that's a delta CT connection will reverse that 30-degree phase shift. That's about the only time you'll see this. I have personally never seen a delta connected CT in real life yet, but I know they do exist in older systems. Okay, so just to summarize what we talk about for CTs, is kind of like, if you need to know anything, it's this. Number one, they're considered in series with the power system. So they go with the line. Never ever fuse a CT, right? CT is meant to have higher current. If you fuse it and the fuse burns, you just blinded yourself from any of the fault analysis. Okay, so never ever put a fuse in the CT circuit. The secondary circuits have all meters in series as well, because it's one single 5-amp loop. Very big, bold. Never open a circuit. Never open a live secondary CT circuit. Or we say never open circuit, or break the switch open, because remember, CT is a giant inductor, and it will store a lot of energy, and you could really hurt yourself because all the energy gets stored up and there's nowhere to go except your hand. Okay. Designed to have 5 amps for normal operations. So look at your low current, design your CT ratio for 5 amps. Make sure you never go above 100 amps in a fault condition. So look at your fault current. Just make sure that you don't ever see 100 amps. Otherwise, you're going to damage the CT. And lastly, select the correct CT accuracy ratio, CT accuracy class based on the burden counts we talked about earlier. So you pretty much do these, and that's 90% of all CT design we do in the power system. Okay. Real quick, I want to put a 3-line diagram in front of you just to say, hey, if I see this, where the CT is, because in an interview, one very common tactic is they'll give you a diagram and say, tell me what you know about this. And at least I want you to know where are all the relays. Where are all the CTs? The easiest way is the bold 3 lines are typically the main power line. So you see ABC up here, ABC. The bolded lines, these are your wires, your phases. Okay. This is your current carrying wires. Okay. Now, on these wires, you'll notice these 3 things. You see there's 3 coils with the dots, 3 coils with the dots. These are your CTs, right? They'll typically be closer circuit breaker. So this square right here, this is your CB. This is your circuit breaker. Notice we have 2 CTs on either side of circuit breakers. Why is that? It's because these are slip-on CTs. Remember, a circuit breaker, you slide the CTs onto bushings. That's what this represents. So it's very common that you'll see 2 CT windings on both sides of every circuit breaker, and we could do our design from there. So just wanted to quick show you 3-line diagram. Where are the CTs? Right there. Okay, so we'll call it, that's all for today for CTs. We'll come back next time. We'll talk about voltage transformers. So I want to say thank you for showing up, and everybody have a good rest of your day. Bye-bye.